Hello, in this lecture we'll answer two questions. In the first question we find out the area of this green shape using two different methods. And in the second question we find out the area of this circle that intersects with this right triangle ACP. So we start with the first question. In the drawing we have quarter circle AOB. We know that line 7 AD equals to line 7 DO. Side OB equals to 2 units in its length. This is right triangle because angle DCB is a right angle. And our task is to find out the area of this green shape. The green shape is actually the right green triangle times DCB. So we have to find out the area of this right green triangle times DCB. So first of all, AOB is a quarter circle, and therefore this is angle AOB, that is a right angle. In addition, OB and OA, they are both the radii of this quarter circle. The radius OB equals to 2, and therefore AO must also equal to 2 units in its length. The radius AO that equals to 2 has been bisected at point D to two halves. The first half AD must be equal to 2 over 2, that is 1. And it is of course equals to the second half of AO, that is DO. That also equals to 1 unit in its length. In the next step, we will implement the Pythagoras theorem on this right triangle DOB. According to the Pythagoras theorem, in any right triangle, the score of the hypotenuse equals to the sum of the scores of the perpendiculars. So in the right triangle DOB, here by PT is evaluation for Pythagoras theorem. In the right triangle DOB, according to the Pythagoras theorem, dB squared, that is the square of the hypotenuse, equals to DO squared plus OB squared. Again, in this right triangle DOB, according to the Pythagoras theorem, the following equation is true. dB squared, that is the square of the hypotenuse, equals to DO squared plus OB squared. dB is the missing side, so we leave it as it is, so it is dB squared equals to DO squared. DO is 1, therefore DO squared is 1 squared, that is 1, plus OB squared. OB is 2, therefore OB squared is 2 squared, that is 4. So in total, if you found out that dB squared equals to 1 plus 4, that is 5. dB squared equals to 5. Here, we will take a root out of this equation, and finding out that dB equals to the square root of 5 units in its length. The length of the hypotenuse dB is equal to the square root of 5 units. In the next step, we will do a construction, that is to say, we will complete this quarter circle to a circle So completing the quarter circle to a circle, and we will extend the radius BO by a straight line until it touches the circle. We define the touching point of the extended radius BO with this circle. This point is point P. BO is a radius, it is absolutely a straight line. We extended the straight line by straight line. When you extend a straight line by straight line, the result PB must be also a straight line. So PB is a straight line. It is a straight line that touches the circle and those 2 points P and B, and therefore PB is a chord that passes from point O, that is the center of the circle, and we know that any chord that passes from the center of the circle must be the diameter of the circle. So PB is the diameter of this circle. Likewise, we'll extend the radius AO by straight line until it touches the circle. When you find the touching point of the extended radius AO with this circle, this point is point Q. So AQ is also the diameter of the circle, exactly for the same reason that PB is the diameter of the circle. Okay, so point O is the center of this circle, point Q is the point of the circle itself, therefore OQ is the radius of this circle, is equals to 2. Likewise, point O is the center of the circle, point P is the point of the circle itself, therefore OP is also the radius of this circle, is equals to 2 units in its length. In the next step, we will extend side CD of this right side DCB until it touches the circle, and the question is where the extended side CD will touch the circle. So we will assume that the extended side CD will not touch the circle at point P, but in this point, point N. So according to our assumption, we have a triangle BCN, this BCN. This is triangle BCN. That is equals to 90 degrees inside. And triangle BCN subtend on chord NB. Again, triangle BCN subtend on this chord NB. Chord NB is definitely not the diameter of the circle because of the fact that chord NB doesn't pass from point O, that is the center of the circle. So in total, we have here triangle BCN, that is equals to 90 degrees inside, and it doesn't subtend on the diameter of the circle. So this is a contradiction to rule 5. Again, on rule 5, according to rule 5, any peripheral angle is equal to 90 degrees in its size must subtend on the diameter of the circle. So in the moment we have a circle, this is peripheral angle MAN, this is equal to 90 degrees inside, and as you can see here, peripheral angle MAN subtend on chord MN, that is the diameter of the circle. So according to this rule 5, any peripheral that equals to 90 degrees inside must subset on the diameter of the circle. While here we found out that now original moment we have peripheral BCN that equals to 90 degrees inside. So according to rule 5, peripheral BCN must subset on the diameter of the circle. But in fact, peripheral BCN subtend on chord BN, this is definitely not the diameter of the circle because of the fact that chord BN doesn't pass through point O, that is the center of this circle. So we have here contradiction to rule 5 because we have peripheral BCN that is a right angle and still it doesn't subset on the diameter of the circle. So due to the contradiction to rule 5, we will cancel this option, that is to say the extended side CD will not touch the circle at point N due to the contradiction to rule 5. In the next step, we will assume that the extended side CD will touch the circle at this point, point M. So according to our assumption, we have here peripheral BCM. This is peripheral BCM. That is equal to 90 degrees inside according to what is given as a question, and still it doesn't subtend on the diameter of the circle. One called peripheral BCM subtend on chord BM, that is definitely not the diameter of the circle. Why chord BM is not the diameter of the circle? Because of the fact that chord BM doesn't pass through point O, that is the center of the circle. Here, if we join points B and M together, by straight line, so peripheral BCM subtend on this chord BM, that is definitely not the diameter of the circle because it doesn't pass through point O, that is the center of the circle. So we have contradiction again because we have peripheral BCM that is equal to 90 degrees inside and still it doesn't subset on the diameter of the circle. So due to the contradiction to rule 5, we cancel the option that the extended side CD will touch the circle at point M. And therefore, we will conclude that the extended side CD will touch the circle at point P, this point. Otherwise, we will have a contradiction to rule 5. In order to avoid the contradiction to rule 5, we must conclude that the extended side CD will touch the circle at point P and not in any other point. Now we don't have a contradiction anymore to rule 5. Why? Because we have peripheral BCP that is equal to 90 degrees in its side according to what is given as the question, and peripheral BCP indeed subtend on the diameter of the circle, that is chord PB. Here we only found out that chord PB is the diameter of the circle, so it is exactly according to rule 5. PB is the diameter of the circle, so PB is the diameter, it is absolutely a straight line. So if you focus on the upper side of the straight line PB at point O, you have the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles from one side of a straight line is equal to 180 degrees. So which angles we have in the upper side of the straight line BP at point O? We have this angle that is the right angle, plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. Actually, those two triangles, they congruent to each other according to side angle and side rule. That is to say, those two sides are both the other of the circle and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, this is side DO, this is the common side that belongs to both triangles. So those two triangles congruent to each other according to side angle and side rule, and therefore they must have also the same hypotenuses. But the hypotenuse of this side is dB, that is equal to the square root of 5 units in itself, and therefore the hypotenuse dP must be also equal to the square root of 5 units in itself, according to the rule that says that corresponding angles in congruent triangles are equal to each other. Those two triangles congruent to each other, and therefore those two corresponding angles must be also equal to each other in their lengths. So BD equals to the square root of 5 units in its length. In the next step, we will implement all 24 in our drawing. Repeat quickly on all 24. According to all 24 is drawn in any circle, so in any circle, if chord AB intersects with chord CD at point O, then the following equation is true. That AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can actually implement all 24 in our drawing. In our drawing, we have chord AQ. AQ is actually the diameter of the circle, and therefore it is a chord. So we have chord AQ that intersects with this chord CP at point D. Again, chord AQ intersects with chord CP at point D. So all the requirements to full 24 are satisfied, and therefore we can implement here all 24. So, write it down. If you found out that in our original drawing, chord AQ intersects with chord CP at point D. And again, now original drawing, chord AQ intersects with chord CP at point D. So all the requirements of all 24 are satisfied, and therefore we can implement all 24. According to all 24, the following equation is true. That AQ times AD times DQ equals to CD times DP. And again, according to all 24, the following equation is true. AD times DQ equals to CD times DP. AD is 1 times DQ. DQ in total equals to 1 plus 2, that is 3. And it is equals to CD. CD is the missing side, so we leave it as it is. Times dp. dp equals to the square root of 5 minutes in its name. So in total, we should find out that 1 times 3 equals to cd times square root of 5. 1 times 3 is 3, so 3 equals to cd times square root of 5. Here we will divide this equation by square root of 5. And finally we get that the missing side CD is equal to 3 over square root of 5 units in its name. So this is the missing side CD. This is equal to 3 over square root of 5 units in its name. So in the next step, we will implement the Pythagoras theorem on this right side or in DCB. So in the right triangle DCB, here by PT is evaluation for Pythagoras theorem. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. This right triangle DCB, dB square, that is the square of the hypotenuse, equals to CD square minus CB square. And again, according to the Pythagoras theorem, and this again I find this CB. dB square, that is the square of the hypotenuse, equals to CD square plus CB square. dB is square root of 5, and therefore dB square is square root of 5 squared, that is 5. and it is equals to CD squared. CD equals to 3 over square root of 5, and therefore CD squared equals to 3 over square root of 5 squared. 3 over square root of 5 squared equals to 3 squared, that is 9, over square root of 5 squared, that is 5. Plus CB squared. CB is the missing sign, so leave this as it is. So in total, if you found out that 5 equals to 9/5 plus CB squared. Here we multiply 5 by 5 and then we divide it by 5 in order to overcome common factor with this number. So 5 times 5 is 25, and we have to divide it by 5. And it is equals to 9/5 plus CB squared. Here we subtract 9/5 from the equation. And we get that 25/5 plus 9/5 is 16/5. Equals to CB squared. Here we take out of the equation. We finally get that the square root of 16 is 4 over square root of 5. So total we found out that the missing side CB is equal to 4 over square root of 5 units instead. This is the missing side CB. That is equals to 4 over square root of 5 units in Islam. Now it is very easy to find out the area of this green shape. This is actually the green right triangle DCB. The area of the green triangle DCB is actually the area of the green shape equals to the base DC times the height CB over 2. Repeat again. The area of the green shape, it is actually the area of the green right triangle DCB. And the area of the green right triangle DCB equals to the base DC times the height CB over 2. We only found out that the base DC equals to 3 over square root of 5. Times the height CB. The height CB equals to 4 over square root of 5 units in Islam. All divided by 2. So in total, the area of the green shape equals to the value of this expression. Here, 3 times 4 is 12 over square root of 5 times square root of 5 is 5 over 2. So here we have 12 over 5 over 2. We move 2 to the denominator, and we get that this expression in total equals to 12 times 5 times 2, that is 10. So in total this expression equals to 10 tenths. In terms of numbers, it is equals to 1.2, so it's in size. And again, the area of this grid shape equals to 1.2 square inches in size. Again, we should know that the area that we're looking for in this question, that is the area of this green shape, is equal to 1.2 square inches in size. So we finish with the first method. In the next step, I present to you another way to find out the area of this green shape. We find out the area of this green shape according to a second method. We already found out that AO equals to OB equals to 2, they are both the area of the circle. That equals to 2 units in its name. AO equals to 2. At point D is the midpoint of AO. So at point D, AO, the radius AO is been bisected into two halves. The first half is 1, and it is of course equals to the second half, DO, that is also 1. AOB is a quarter circle, and therefore this is a right angle. In the next step, we will do a construction, that is to say, we will complete this quarter circle to a semicircle. So complete the quarter circle to a semicircle. We will extend the radius VO by side line until it touches the semicircle. And we define the touching point of the extended radius VO with this semicircle. This point is point P. Exactly as we did in the first method. When you extend a straight line by a straight line, the result is a straight line. So BO is the radius of this circle, that is a straight line. We extend the radius BO, this is a straight line by straight line, and the result is BP. So BP is a straight line that touches the circle in those two, the semicircle in those 2 points, B and P. Therefore, BP is a chord that passes from point O, that is the center of the semicircle, and therefore BP is the diameter of the semicircle. In the next step, we extend side CD by side line until it touches the circle and the semicircle. We only found out that the extended side CD must touch the circle at the semicircle or circle, doesn't matter, at point P and not in any other point due to the conversion to Rule 5. So the extended side CD must touch the semicircle at point P. Now we don't have conversion to Rule 5 anymore because we have here peripheral BCP that equals to 90 degrees inside according to what's given us a question, and peripheral BCP subtend on PB, that is the diameter of this semicircle, exactly according to Rule 5. So point O is the center of the semicircle, point P is the point of the semicircle itself, therefore OP is the radius of this semicircle, is equals to 2. If we implement the Pythagoras theorem on this, actually this angle equals to 90 degrees according to Rule 3. I already explained in the first method that this angle must be equal to 90 degrees according to Rule 3, so I will not repeat on the same explanation here. We only found out that according to the Pythagoras theorem, in this right triangle DOP, the opponent PD equals to the square root of 5 units in its length. In the next step, we will focus on this right triangle PDO. We define this angle OPD is alpha. And we will continue to focus on this small right triangle PDO. This small right triangle PDO, this angle equals to alpha, this angle equals to 90 degrees, and therefore this spread this angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right triangle PCB, this angle equals to alpha. This angle equals to 90 degrees according to what is given as a question, and therefore this spread missing angle must be equal to 90 degrees minus alpha, according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. So this spread missing angle must be equal to 90 degrees minus alpha. In the next step, we prove that the small right triangle PDO is similar to this big right triangle PCB. So when those two right triangles are similar to each other. First of all, this is the angle alpha, this is the common angle that belongs to both triangles. Angle alpha definitely belongs to the small right triangle PDO, and angle alpha definitely belongs to the big right triangle PCB. So we can write down that angle alpha equals to itself as a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees once alpha and therefore they are equal to each other. So in total, we found that all the figures of this small right triangle PDO are corresponding equal to all the figures of this big right triangle PCB. And therefore, those two right triangles are similar to each other according to angle similarity rule. So write it down. This is the small right triangle PDO. And it's similar. This is the sign of similar to this big right triangle PCB. According to angle similarity rule. Okay, again, actually found out that the small right triangle PDO is similar to the big right triangle PCB according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side PD of this small right triangle POD or side PB of this big right triangle PBC is equal to side DO of this small right triangle PDO over side CB of this big right triangle PCB, and it is also equal to side PO of this small right triangle POD over side PC of this big right triangle PCB. So I write it down. Yes, for the fact that the small right triangle PDO is similar to the big right triangle PCB, we derive that the following relationship exists between their sides. We derive that side PD of the small right triangle POD or side PB of the big right triangle PCB is equal to side DO of the small right triangle PDO or side CB of the big right triangle PCB, and it is also equal to side PO of the small right triangle POD or side PC of the big right triangle PCB. PD equals to the square root of 5. over PB. PB in total equals to 2 plus 2, that is 4. This is the diameter of the circle, and it is equals to 4 units in its length. And it is equals to DO. DO is 1 over CB. CB is the missing side, so yes, it is. And it is equals to PO. PO is 2 over PC. PC in total equals to the square root of 5 plus DC. In total, if you found out that square root of 5 over 4 equals to 1 over CB equals to 2 over square root of 5 plus DC. Those two sides of the equation are equal to each other, therefore we get the equation 1 from those two sides that are equal to each other. So according to equation 1, we get that square root of 5 over 4 equals to 1 over CB. Here we multiply this equation, we cross multiply this equation in equation 1, and get that according to equation 1, square root of 5 times CB equals to 4. Here we divide this equation 1 by square root of 5. If I get that according to this equation 1, CB equals to 4 over square root of 5 units in its length. So okay, this is side CB that is equals to 4 over square root of 5 units in its length. Those two sides of the equation are also equal to each other, so we get equation 2 from those two sides that are equal to each other. According to equation 2, we get that square root of 5 over 4 equals to 2 over square root of 5 plus DC. So write it down. Get square root of 5 over 4 equals to 2 over square root of 5 plus DC. Here we will cross multiply this equation 2, and get that according to this equation 2, 4 times 2 is 8, equals to the square root of 5 times square root of 5 plus DC. So according to this equation 2, we have to find out that 8 equals to square root of 5 times square root of 5 is 5, plus square root of 5 times DC. Here we will subtract 5 from this equation, equation 2. And get that according to this equation, equation 2, eight minus 5 is 3, so 3 equals to square root of 5 times DC. Here we will divide this equation 2 by square root of 5. And I get that according to this equation 2, the missing side DC, in total is equal to 3 or square root of 5 units in its length. This is the missing side DC. This is equals to 3 over square root of 5 units in its length. Now it is very easy to find out the area of this green shape. The area of the green shape in total it is equals to the area of this green rectangle DCB. And again, the area of the green shape, that is the area that we are looking for in this question. Is equals to the area of the right triangle DCB. The area of the right triangle DCB must be equal to the base DC times the height CB over 2. And again, the area of this right triangle DCB in total must be equal to the base DC times the height CB over 2. DC equals to 3 over square root of 5 times CB. CB equals to 4 over square root of 5 divided by 2. So in total, if you found out that the area of the green shape equals to 3 over square root of 5 times 4 over square root of 5 divided by 2. 3 times 4 is 12, and square root of 5 times square root of 5 is 5. So here we have 12 over 5 over 2. So here we remove 2 to the denominator for this expression, and you get that the area of the green shape in total equals to 12 times 5 times 2. 12 over 5 times 2. 5 times 2 is 10, so in total this expression equals to 12 over 10. And 12 over 10 is 1.2 square units in size. So in both methods, if you found out that the area of this green shape is equal to 1.2 square units in size. So we finish with the second method, and with the first question. In the next step, I will present you the second question of this lecture, and we solve the second question. Our task in this second question is to find out the area of this circle that intersects with this right triangle ACP. This is angle ACP, this is the right angle. This is line segment BC. This is equals to 1 unit in Islam. This is line segment PC. This is equals to 4 units in Islam. In the drawing, we have also the common exam point P. From this common exam point P, we have two tangents to this circle, tangent PA and tangent PB. Again, our task is to find out the area of this circle. So first of all, we can implement here rule 2. So repeat quickly on rule 2 and we will implement the rule in our drawing. According to rule 2, the lengths of two tangents from a common exam point to a circle are equal. In the drawing, we have a circle. This is the common exam point P. From this common exam point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other in their lengths. That is to say, the length of tangent PA is equal to the length of tangent PB, or PA equals to PB. So we can actually implement rule 2 in our drawing. Like in our drawing, this is the common exam point P. From this common exam point P, we have two tangents to this circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say, PA equals to PB. So, I write it down. From the common exam point P, we have two tangents to this circle. Tangent PA and tangent PB, and according to rule 2, they are equal to each other. And again, according to rule 2, tangent PA equals to tangent PB in its length. But it is given the question that the length of tangent PB in total equals to 1 plus 4, that is 5. So we can write here that PB equals to 5, and from this equation PA equals to PB equals to 5, we derive that PA must be also equal to 5 units in its length. This is tangent PA is equals to 5 units in its length. In the next step, we will implement the Pythagoras theorem on this right triangle ACP. Here by PT is the operation for Pythagoras theorem. So according to the Pythagoras theorem, in this right triangle ACP, AP squared, that is the square of the hypotenuse, equals to AC squared plus CP squared. And again, this I find ACP according to the Pythagoras theorem. AP squared, that is the square of the hypotenuse, equals to AC squared plus CP squared. AP is 5, and therefore AP squared is 5 squared, that is 25. And it is equals to AC squared. AC is the missing side, so we leave it as it is. So it is AC squared plus CP squared. CP is 4, therefore CP squared is 4 squared, that is 16. So if you know that 25 equals to AC squared plus 16. Here we subtract 16 from the equation, and I get that AC squared equals to 25 minus 16 is 9. So AC squared equals to 9. Here we take a root out of the equation, and I get that the missing side AC is equal to the square root of 9, that is 3. So AC equals to 3 units in its length. This is side AC, this side ACP, and it is equals to 3 units in its length. In the next step, we define the center of this circle. This point is point O, and we define the radius of this circle as x. And we will join points O and B together by straight line. Point O is the center of this circle, point B is the point of the circle itself, therefore OB is the radius of this circle. This equals to x according to our definition. The radius OB is equals to x, the radius OB is drawn to point B, that is the point of tendency of tangent PB with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees according to rule 1. PB is a tangent, so PB is a tangent, it is absolutely a straight line. So if you focus on the upper side of the straight line PB at point C, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line PB at point C? We have this angle that is right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will do a construction, that is to say from point O, that is the center of this angle, we will do perpendicular on AC. Again, from point O, we will do perpendicular on AC. So here, this angle equals to 90 degrees on its side, and this angle also equals to 90 degrees on its side, according to our construction. We will define the tangent point of the perpendicular from point B, and AC, this point is point M. So, by doing this construction, we can do quadrilateral OMCB. Yeah, this is quadrilateral OMCB. Inside this quadrilateral OMCB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, must be equal to 360 degrees, according to the rule that says that the sum of the angles in every quadrilateral is equal to 360 degrees, and therefore this fourth missing angle is equal to 90 degrees in its size. So in quadrilateral OMCB we have 4 right angles, and therefore can relate to quadrilateral OMCB is a right angle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle OMCB, side OM must be equal to the opposite side CB, but CB is 1, and therefore this opposite side OM must be equal to 1 unit in itself. Likewise, according to the same rule, in the same rectangle OMCB, side OB must be equal to the opposite side MC, but OB is X, and therefore the opposite side MC must be also equal to X units in itself. So what is left of this missing line 797 AM? AM equals to AC minus MC. So write it down. I should hold that the left of side AM total is equal to AC minus MC. So AM in total equals to AC is 3, minus MC is X. So total we found out that AM equals to 3 minus X units in itself. The next step, we join points O and A together by a straight line. Point O is the center of the circle, point A is the point of the circle itself, therefore OA is the radius of the circle, is equals to X. So in the next step, we will implement the Pythagoras theorem on this right hand triangle, triangle AOM. On this right triangle AOM, here by PT is information from Pythagoras theorem. This right triangle AOM, according to the Pythagoras theorem, AO squared, that is the square of the hypotenuse, equals to AM squared plus OM squared. And again, according to the Pythagoras theorem, this right triangle AOM, the following version is true. That AO squared, that is the square of the hypotenuse, equals to AM squared plus OM squared. AO equals to X, and therefore AO squared equals to X squared, and it is equals to AM squared. AM is 3 minus X, and therefore AM squared is 3 minus X squared. Plus OM squared. OM is 1, therefore OM squared is 1 squared, this is 1. So in total, if you found out that according to the Pythagoras theorem, this AOM, X squared equals to 3 minus X squared plus 1. So X squared equals to 3 minus X squared. 3 minus x squared equals to 3 squared, that is 9, plus x squared, minus 2 times 3 times x, that is minus 6x. And we have here also plus 1. Here we have x squared on both sides of the equation, so x squared gets cancelled. So you can set x squared on the side of the equation left with nothing, that is to say 0. While on the other side of the equation we have 9 plus 1, that is 10, or 6x. Here we will add 6x to this equation. And finally get that 0 plus 6x is 6x equals to 10. Six x equals to 10. Here we divide this equation by 2. So you get that 6x over 2 is 3x equals to 10 over 2, that is 5. So 3x equals to 5. Here we divide this equation by 3. And finally we get that x equals to 5/3. And again, if you found out that x equals to 5/3, x is the radius of this circle, and our task is to find out the area of this circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. And again, the area of any circle equals to pi times the radius of the circle squared. So the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle is x, so and the radius squared is it is x squared. So in total, the area of our circle must be equal to pi times x squared. So it is pi times x squared. X is 3/3, and therefore x squared is 3/3 squared. It is actually 25/9. So in total, the answer of the question is that the area of this circle, this is the area that we're looking for, is equal to either 25/9 square roots inside, or in terms of numbers, it is equal to 8.73 square roots inside. And again, I should know that the area that you're looking for in this question, that is the area of this circle, equals to either 25/9 square roots inside, or in terms of numbers, it is equals to 8.73 square roots inside. So the next step of the lecture, we start the repetition of the first question, and then we get to the solution of this second question. Our task in the first question is to find out the area of this green shape. So in the drawing we have a quarter circle, AOB is a quarter circle. We know that line 7 AD equals to line 7 DO. This is side OB. This is equals to 2 units in itself. This is angle DCB. This is a right angle. So our task is to find out the area of this green shape. The green shape is actually the right green triangle DCB. So we have to find out the area of this right green triangle DCB. We start with the first method. First of all, we know that AOB is a quarter circle and therefore this is a right angle. Likewise, the two of the area of the quarter circle are OB and OA. The radius OB equals to 2 and therefore AO is also the radius is equals to 2. At point D, the radius AO is bisected into 2 halves. Each half must be of course equals to 1, because in total it is 2. So AD equals to 1 and DO also equals to 1. In the next step we implemented the Pythagoras theorem on this right line DOB. According to the Pythagoras theorem, in a right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this right angle DOB, DB squared, that is the square of the hypotenuse, equals to DO square plus OB square. And again, in this right angle DOB, according to the Pythagoras theorem, DB squared, that is the square of the hypotenuse, equals to DO square plus OB square. DB is 1, therefore DB square is 1 squared, that is 1, plus DO square, plus DB, plus OB square. OB is 2, therefore OB square is 2 squared, that is 4. So we should found out that DB square equals to 1 plus 4, that is 5. So DB square equals to 5. Here we took out of the equation and found out that the hypotenuse DB equals to the square root of 5 units in its length. This is the hypotenuse DB. This equals to the square root of 5 units in its length. In the next step, we completed this quarter circle to a circle and we extended the radius AO by side line until it touches the circle. We define the touching point of the extended radius AO with this circle. This point is point Q. When you extend AO is a radius that is absolutely a straight line. When you extend a straight line by straight line, the result is a straight line. So AQ is also a straight line, but AQ is a straight line that touches the circle 2 points A and Q. Therefore, AQ is a chord that passes from point O, that is the center of this circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, AQ is the diameter of the circle, point O is the center of the circle, point Q is the point of the circle itself, and therefore OQ is the radius of the circle, that equals to 2. Likewise, we extended the radius BO by straight line until it touches the circle, and we find the touching point with the extended radius BO with this circle. This point is point P. For the same reason that AQ is the diameter of the circle, BP must be also the diameter of the circle. Again, BP is the diameter of the circle. Let's repeat on the same explanation. So, in the next step, we extended side CD of this triangle by straight line until it touches the circle. But the question is where the extended side CD will touch the circle. We assume that the extended side CD will touch the circle at this point N. So according to our assumption, we have a triangle BCN. This is equals to 90 degrees inside according to what is given in the question. triangle BCN subtend on this code BN. Code BN is definitely not the diameter of the circle because of the fact that code BN doesn't pass through point O, that is the center of the circle. Therefore, we have here contradiction to all 5 because we have triangle BCN that is equal to 90 degrees inside and still it doesn't subtend on the diameter of the circle. Because code BN is definitely not the diameter of the circle. So due to the contradiction to all 5, we cancel this option. That is to say, the extended side CD cannot touch the circle at this point M. In the next step, we assume that the extended side CD will touch the circle at this point M. So according to our assumption, we have triangle BCM. This is equal to 90 degrees inside, and triangle BCM subtend on this chord called MB. Chord MB is definitely not the diameter of the circle because of the fact that chord MB doesn't pass for point O, that is the center of the circle. Again, we have contradiction to all 5 because we have triangle BCM that is equal to 90 degrees inside and still it doesn't subtend on the diameter of the circle because chord BM is not the diameter of the circle. So due to the contradiction to all 5, we cancel the option that the extended side CD will touch the circle at this point M. And therefore, we must conclude that the extended side CD will touch the circle at point P and not in any other point due to the contradiction to all 5. So, therefore, we have here triangle BCP is equal to 90 degrees inside, and indeed triangle BCP subtend on chord PB, that is the diameter of the circle, exactly according to all 5. In the next step, we know that PB is the diameter of this circle, so PB is the diameter, it is absolutely a side line. So if we focus on the upper side of the side line PB at point O, here the sum of the angles must be equal to 180 degrees according to all 3. So which angles we have at the upper side of the side line PB at point O, we have this angle that is the right angle, plus this missing angle, we told them the sum of those angles must be equal to 180 degrees according to all 3. Therefore this missing angle must be equal to 90 degrees in size. So we have here the right triangle POB. Point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of the circle, that equals to 2. Actually those two right triangles can go into each other, and therefore they have also the same hypotenuses. DB is square root of 5, and therefore the hypotenuse PD must be also equal to the square root of 5 units in its length. In the next step, we implemented all 24 in our drawing. Let's paint quickly on all 24. According to all 24, all 24 is shown in any circle, so in any circle, of course, the intersect with chord CD at point O, then the following equation is true. AO times BO equals to CO times DO. So, in the drawing, we have a circle. This is called AB that intersects with chord CD at point O. Whenever you have two chords that intersect with each other inside the circle, you can implement this all 24. In this drawing, the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can implement all 24 in our drawing. In our drawing, we have chord AQ. AQ is the diameter of the circle, and therefore it is definitely a chord. It is the biggest chord in the circle. So chord AQ intersects with this chord CP at point D. Again, chord AQ intersects with this chord CP at point D. CP is also a chord. Why? Because we extended the straight line CD by straight line. When you extend the straight line by straight line, the result CP is also a straight line. So CP is a straight line that touches the circle at 2 points, C and P. Therefore, CP is a chord because it is a straight line that touches the circle at those 2 points, and therefore it must be a chord. So in total, we should find out that chord AQ intersects with chord CP at point D. Repeat again, chord AQ intersects with chord CP at point D. So all the requirements of all 24 are satisfied, and therefore can implement all 24. Repeat again, now already on drawing, we have chord AQ that intersects with chord CP at point D. So according to all 24, the following equation is true, that AD times DQ equals to CD times DP. Again, AD times DQ equals to CD times DP. AD is 1 times DQ. DQ in total is 1 plus 2, that is 3. And it is equals to CD. CD is the missing side, so we leave it as it is, times DP. DP is equals to the square root of 5 minutes in itself. So in total, we should find out that according to rule 24, 1 times 3 equals to CD times square root of 5. 1 times 3 is 3, so 3 equals to CD over square root of 5. Here we divided the equation by square root of 5 and find out that the missing side CD equals to 3 over square root of 5 minutes in itself. This is the missing side CD. This is equals to 3 over square root of 5 minutes in itself. In the next step, we implemented the Pythagoras theorem on this right triangle times DCB. According to the Pythagoras theorem, this right triangle DCB, dB squared, that is the square, this right triangle DOB. Okay, we implemented the Pythagoras theorem on this right triangle DCB. This right triangle DCB, according to the Pythagoras theorem, dB squared, that is the square of the hypotenuse, equals to DC square plus CB square. Again, this right triangle DCB, dB square equals to DC square plus CB square. So again, right triangle DCB, according to the Pythagoras theorem, dB square equals to CD square plus CB square. dB equals to the square root of 5, and therefore dB square is square root of 5 squared, that is 5. And it is equals to CB square. CB is the missing side, so leave it as it is, plus CD square. CD equals to 3 over square root of 5, therefore CD square equals to 3 over square root of 5 squared. This is 9/5. So in total, we should find out that 5 equals to 9/5 plus CB square. We will multiply 5 by 5 and then we divide it by 5 in order to overcome a factor of this number. So 5 times 5 is 25 over 5 equals to 9/5 plus CB square. Here we subtract 9/5 from this equation, and find out that 25/5 minus 9/5 equals to 16/5 equals to CB square. So 16/5 equals to CB square. Here we took out the equation and found out that the missing side CB equals to the square root of 16, that is 4 over square root of 5. So this is the missing side CB. This is equals to 4 over square root of 5 minutes in itself. Our task is to find out the area of this ring-shape. This ring-shape is actually the right triangle DCB. So we have to find out the area of the right triangle DCB. So again, our task is to find out the area of the ring-shape. The ring-shape is actually the area of the right triangle DCB. And the area of this right triangle DCB equals to the base DC times the height CB over 2. And again, the area of this right triangle DCB in total is equals to the base DC times the height CB over 2. DC is 3 over square root of 5. CB is 4 over square root of 5 divided by 2. 3 times 4 is 12. Square root of 5 times square root of 5 is 5 over 2. So here we move 2 to the denominator. And this expression in total equals to 12 over 5 times 2, that is 10. So it is 12 over 10. 12 over 10 is 1.2 square root inside. So in total, we found out that the area that we are looking for in this question, that is the area of this green shape, in total it is equal to 1.2 square root in size. So finish with the first method. In the next step, I fit on the solution according to the second method. We find out the area of this green shape according to the second method. I fit on the solution. In the first method, we only found out that AO and OB are above the area of this quarter circle, and therefore each of them is equal to 2 units in itself. At point D, the radius AO is bisected into 2 halves. The first half, AD is 1, and then it is of course equal to the second half of the radius, it is also 1. DO is also 1. AOB is a quarter circle, and therefore this is a right angle. In the next step, we completed this quarter circle to a semicircle, and then we extended the radius BO by sideline until it touches the circle at this point P. PB, because of the fact that this is a semicircle, PB is the diameter of the semicircle, and we extended side CD by sideline, and I've only proved in the first method that the extended side CD must touch the circle or the semicircle at this point P, and not in any other point due to the contradiction to rule 5. Now we don't have contradiction to rule 5 anymore. Why? Because we have triangle BCP that is equal to 90 degrees inside, and it indeed subset on CB, on PB, that is the diameter of the semicircle, exactly according to rule 5. So we only proved that in the first method this angle equals to 90 degrees inside according to rule 3. So in this right triangle DPO, 1 square plus 2 square equals to PD square, so PD square equals to 5, and therefore PD equals to the square root of 5 units in its length. In the next step, we define this angle DPO. In the right triangle DPO is alpha, so in the right triangle DPO, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first BC angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, in the big right triangle CPB, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first BC angle must be equal to 90 degrees minus alpha according to the sum that said that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that the small right triangle PDO is similar to the big right triangle PCB according to angle similarity rule. So, why the small right triangle PDO is similar to the big right triangle PCB? First of all, this is angle alpha, that is a common angle that belongs to both triangles. So we can write down that angle alpha equals to itself is a common angle that belongs to both triangles. Likewise, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So we can prove that all the figures of this small right triangle PDO are corresponding equal to all the figures of this big right triangle PCB. Therefore, those two right triangles are similar to each other according to angle similarity rule. And again, if we found out that the small right triangle PDO is similar, this is the sum of similar to the big right triangle PCB according to angle similarity rule. And from the fact that those two right triangles are similar to each other, the right triangle PDO is similar to the big right triangle PCB, we derive that the following relationship exists between their sides. We derive that side PD of the small right triangle or side PB of the big triangle equals to side DO of the small triangle or side CB of the big triangle, and it is also equals to side PO of the small triangle or side PC of the big triangle. PD is equal to 5, PB is 4, DO is 1, CB is the missing side, so it is, PO is 2. This is side PC, in total side PC equals to the square root of 5 plus DC. Yeah. PC equals to the square root of 5 plus DC. And again, PC equals to the square root of 5 plus DC. So in total, if you found out that square root of 5 over 4 equals to 1 over CB equals to 2 over square root of 5 plus DC. Those two sides of the equation are equal to each other, so we get the equation 1 from those two sides that are equal to each other. So according to equation 1, square root of 5 over 4, square root of 5 over 4 equals to 1 over CB. And square root of 5 over 4 equals to 1 over CB. Here we cross multiply this equation. If I found out that 1 times 4 is 4 equals to the square root of 5 times CB. Square root of 5 times CB equals to 4. Here we divided the equation by square root of 5 and I found out that the limit inside CB equals to 4 over square root of 5 units in its length. This is the limit inside CB. This equals to 4 over square root of 5 units in its length. Those two sides of the equation are equal to each other, therefore we get the equation 2 from those two sides that are equal to each other. According to equation 2, square root of 5 over 4, square root of 5 over 4 equals to 2 over square root of 5 plus DC. Okay, again, according to equation 2, square root of 5 over 4, square root of 5 over 4 equals to 2 over square root of 5 plus DC. Here we cross multiply this equation, so we found out that 2 times 4 is 8, equals to the square root of 5 times square root of 5 plus DC. We open the brackets of this expression, and in total we found out that 8 equals to square root of 5 times square root of 5 is 5, and square root of 5 times DC is square root of 5 times DC. So in total, according to equation 2, we found out that 8 equals to 5 plus square root of 5 plus this, plus square root of 5 plus DC. Here we subtract 5 from the equation, we found out that 8 minus 5 is 3 equals to square root of 5 times DC. Here we divide this equation by square root of 5 and found out that the missing sign DC equals to 3 over square root of 5 units inside. Okay, in the end we found out that this is the missing side DC is equals to 3 over square root of 5 units inside. Our test is to find out the area of this green shape. The green shape is actually the right triangle DCB. So the area of the green shape is actually the area of the green right triangle DCB. So we have to find out the area of the green right triangle DCB. The area of the green right triangle DCB must be equal to the base DC times the height CB over 2. Because again, the area of the green right triangle DCB in total must be equal to the base DC times the height CB over 2. DC is 4 over square root of 5 times CB is 4 over square root of 5 divided by 2. 3 times 4 is 12. Square root of 5 times square root of 5 is 5 over 2. We move 2 to the denominator of this expression. So in total this expression equals to 12 over 5 times 2. 5 times 2 is 10, so in total this expression equals to 12 times. 12 times is 1.2 square units in size. So in both methods we found out that the area that we're looking for in this equation, that is the area of this green shape, is equal to 1.2 square units in size. So we finish to repeat on the first question. In the next step I repeat on the solution of the second question. In the second question, our task is to find out the area of this circle. So in the drawing, we have a circle that intersects with this right triangle ACP, those 2 points. In addition, we know that this is line 7BC, this is equals to 1 unit in itself. This is line 7CP, this is equals to 4 units in itself. This is angle ACB, that is the right angle. In addition, we have this is the common sum point P. From this common sum point P, we have 2 tangents to this circle, tangent PB and tangent PA. And our task is to find out the area of this circle. So first of all, we implemented all 2 in our drawing. This is the common sum point P. From this common sum point P, we have 2 tangents to this circle, tangent PA and tangent PB. And according to all 2, they are equal to each other. That is to say P equals to PB. Repeat again on all 2. According to all 2, the lengths of 2 tangents from the common sum point to a circle are equal. In the drawing, the circle, this is the common sum point P. From this common sum point P, we have 2 tangents to this circle, tangent PA and tangent PB. And according to this all 2, they are equal to each other. That is to say PA equals to PB. From the common sum point P, we have 2 tangents to this circle, tangent PA and tangent PB. And according to all 2, they are equal to each other. That is to say PA equals to PB. If we focus on the common sum point P, we have 2 tangents to the circle, tangent PA and tangent PB. According to all 2, they are equal to each other. That is to say P equals to PB. But it is given as a question that the length of this tangent PB in total equals to 1 plus 4, that is 5. So we can write down that PB equals to 5, For this equation, PA equals to PB equals to 5. We will derive that PA also equals to 5 units in Islam. This is tangent PA. This equals to 5 units in Islam. The next step, we plotted the Pythagoras theorem on this line ACP. According to the Pythagoras theorem, AP squared equals to AC squared plus CP squared. And again, in this line ACP, according to the Pythagoras theorem, AP squared equals to AC squared plus CP squared. AP is 5, therefore AP squared is 5 squared, that is 25. And it is equals to AC squared. AC is the missing side, so limit is it is, so it is AC squared plus CP squared. CP is 4, therefore CP squared is 4 squared, that is 16. So in total, we now know that 25 equals to AC squared plus 16. Here we subtract 16 from this equation, and find out that AC squared equals to 25 minus 16, that is 9. So AC squared equals to 9. Here we took out of the equation, and find out that the missing side AC equals to the square root of 9, that is 3. This is the missing side AC, is equals to 3 units in its length. In the next step, we define the center of this circle, this point as point O. We define the radius of this circle as x. And we join points O and B together by side line. Point O is the center of the circle, point B is the point of the circle itself, therefore B is the radius of the circle, is equals to x. The radius of B is equals to x. The radius of B is going to point B. It is the point of tendency of tangent PB with this circle. And whenever your radius is going to the point of tendency, then tangent PB will be perpendicular to radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees according to rule 1. PB is the tangent to the circle, therefore it is absolutely straight line. So if you focus on the upper side of the straight line PB at point C, if the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have the upper side of the straight line PB at point C, we have this angle that is the right angle, plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. In the next step, we did the construction, that is to say from point O, we do perpendicular on AC. Again, from point O, we do perpendicular on AC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AC. This point is point M. When doing this construction, we can do the quadrangle OMCB. Quadrangle OMCB, we have 1, 2 radius. The sum of 3 radius is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total must be equal to 360 degrees. According to the rule that states that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in size. So in quadrangle OMCB we have 4 angles, and therefore can relate to quadrangle OMCB is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So rectangle OMCB, side BC must be equal to the opposite side OM. But BC is 1, therefore the opposite side OM must be also equal to 1 unit in its length. Likewise, according to the sum of the sum of rectangle OMCB, side OB must be equal to the opposite side MC. But OP is x, therefore the opposite side MC must be also equal to x units in its length. In the next step, we join points O and A together by side line. Point O is the center of the circle, point A is the point of the circle itself, therefore OM is the radius of the circle, that is equal to x. What is the ref of line center AM? From the drawing, it is very easy to say that AM is totally equals to AC minus MC. Again, AM equals to AC minus MC. So AM equals to AC, that is 3, minus MC, that is x. So in total, AM equals to 3 minus x units in its length. In the next step, we plot the Pythagoras theorem on this right line A and B. According to the Pythagoras theorem, in this right line A and B, AO squared is the square of the hypotenuse equals to AM squared plus MO squared. In the right line AOM, according to the Pythagoras theorem, AO squared is the square of the hypotenuse equals to AM squared plus OM squared. AO is x, therefore AO squared is x squared, and it equals to AM squared. AM is 3 minus x, therefore AM squared is 3 minus x squared plus OM squared. OM is 1, therefore OM squared is 1 squared, that is 1. So in total, if you want to know that x squared equals to 3 minus x squared plus 1. So x squared equals to 3 minus x squared. 3 minus x squared equals to 3 squared, that is 9, plus x squared minus 2 times 3 times x, that is minus 6x plus 1. Here we have x squared on both sides of the equation, so x squared will get cancelled, and we cancel x squared on this side of the equation, we have nothing, that is to say 0. When on the other side of the equation, we have 9 plus 1, that is 10 minus 6x. So in total, if you found out that 0 equals to 10 minus 6x, Here we added 10 to this equation, and find out that 6x equals to 10. Here we divided this equation by 2 and find out that 6x over 2 is 2x, and 10 over 2 is 5, so 3x equals to 5. Here we divided this equation by 3 and find out that x, that is the radius of the second, equals to 3 thirds. The radius of this second, x equals to 5 thirds. X equals to 5 thirds. Our test is to find out the area of the circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared, and therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle is x, therefore the radius squared is x squared. So in total, the area of our circle must be equal to pi x squared. But we just now found out that x equals to 5 thirds. If x equals to 5 thirds, it means that x squared must be equal to 5 thirds squared. So in total, the area of our circle must be equal to pi times 5 thirds squared. 5 thirds squared equals to 5 squared, that is 25, over 3 squared, that is 9. So in total, the area of our circle must be equal to either 25 pi over 9 square units in size, or in terms of numbers, the area of our circle must be equal to 8.73 square units in its size. So again, the area of this circle, that is the area that we're looking for this question, it is equal to either 25 pi over 9 square units in size, or in terms of numbers, the area of this circle equals to 8.73 square units in its size. Okay, thank you very much.